When considering the Earth as a magnetic dipole, it's easy to imagine that variations in the geomagnetic field are symmetric between north and south. However, there have been several measurements going back several decades that have found certain signs of asymmetry, like different latitudes for the auroral irregularities between north and south, or a difference in rheometer absorption of cosmic radio noise, and spatial and temporal offsets in the development of auroral structures and when the substorm onset occurs. Now, this is a matter of some concern, since most of our measurements and our technological infrastructure are in the north of the planet. And so it has come to be that substorm models tend to rely on northern measurements, assuming that the south follows suit. There have also been indications recently that geomagnetically induced currents are less intense in the south compared to the north. But so far, comparative measurements have been sparse, usually focusing on small time periods or specific events. Mostly between there have been so few magnetometer stations in the south compared to the north, as Konstantinos mentioned earlier, making it difficult to obtain large-scale comparisons. This has somewhat been mitigated recently, and we decided to dive deeper into the issue, making use of the SuperMag network of magnetometer networks, which is an online collection of ground magnetometer data from all around the globe, which are mostly available at a 1-minute sampling rate. Some are 1 second, but not enough in the south, so that won't concern us here. Now, looking at the sample that we had, we decided not to restrict ourselves to a specific event or two, but to perform a statistical analysis over a whole solar cycle. So looking at 2009 to 2019, we found 5 southern magnetometers, which have been in continuous or near continuous operation for those 11 years, and which have conjugate points in the north that are fairly close to northern magnetometers that have also had very good coverage during the same time period. Now, we don't have perfect conjunctions. Well, the Earth is big, so it's really hard to get that with magnetometers semi-randomly being all over the place. But the ones that we found are fairly close. Let's see. Now, of this 5 series of stations, 2 of them, Dome Concordia and Macquarie Island, are at fairly high geomagnetic latitudes. Their L equals 5.8 and 5.4 respectively. And their counterparts are in Canada and in Alaska. And we also found 3 stations that are somewhat lower latitudes at around 2.5 to 3, with also counterparts in the US and Russia. Dome Concordia is the station that we found most interesting because of the counterparts in Canada. And you can see that it falls between the Churchill line of the Charisma network and the Sanikiluaq station a bit further to the west. So we decided to use both those stations to fill data gaps and have a better overview of the situation, especially in 2012 and 2019, where there seems to be less data in Gillam than in Sanikiluaq. And you can see the availability up here. The worst set of data in respect of availability is Kiana and Macquarie Island, which is in Alaska and the South Pacific, where Kiana has fairly low availability. But everything else seems to be good enough. Now, because of the 1-minute sampling rate, we could only fully resolve ULF power in the PC5 frequency range by performing fast Fourier transforms. Here you can see the north to south power ratios over the course of 1 solar cycle for Gillam versus Dome Concordia and Sanikiluaq versus Dome Concordia. You can notice a strong seasonal dependence and also a weak solar cycle dependence. And just by looking at these figures, you can readily see that there generally seems to be more power in the north than in the south. So that is a big picture. Let's see if we can glean any more detail from subsets of that data. Here we plot the power versus power for Gillam and Dome Concordia close to the solar minimum on the left in 2009 and close to the solar maximum on the right in 2015 Well, the maximum was actually 2014, but we didn't have enough data in Gilam, so we picked 2015 for our comparisons. The black lines in the middle of the density plot are the medians, and the dashed lines around them are the upper and lower quartiles. We can see that near the solar minimum, there is rough parity in power between the hemispheres. But during the solar maximum, roughly 75% of the time, there is more power in the north than in the south, and often a lot more power in the north than in the south. Now, looking at winter in 2009, the trend is a bit reversed. In solar minimum, there's actually a bit more power in the south, while in a solar maximum, there is roughly parity with maybe a bit more power in the north. And yeah, this solar cycle dependence is the reason why I made that comment to Konstantinos earlier, because he was looking at 2015, but 2009 might be a bit different. Now, the other set of hydrogen stations, they are located at similar L, but they are a bit different. There seems to be more power overall in the north. Here we see in the summer and in the winter, except for some aberrations at very high power in 2015. And these plots are a lot more streamlined. There isn't as much scatter as in the other stations. Now, there are three caveats here, one of which I'll get to later. But also the difference in L between the stations is a bit higher than in the previous case. So the northern station is about an L 0.5 higher than the southern station, which may account for some of the difference in behavior. And also, Kian had low availability in 2015, especially in the winter, so the statistic isn't as good. Now, going to an L of 3 or less, we see a much smaller spread of power, particularly in quiet years, both in the summer and in the winter. There's a consistent northern preference in 2015, and well, a bit also in 2009, but not as distinct. Although that shouldn't affect the total power as much as in Gilam because of the lower spread. And if you look at Fredericton and well, the other station at the south, this is the only case where the southern station is actually at slightly higher L than the northern one, at 2.5 in the south versus 2.2 in the north. And yet there's still more power in the north during solar maximum. And we have rough parity in solar minimum. Sorry, this time's confused. And finally, zoom again in Irewell, I find a bit dubious, because there's a big spread in South Pacific station in 2009, and this weird structure at 0 in 2015, which makes me not trust them very much, so I won't be using them as much as the other stations. Now, by taking the monthly mean of PC5 power in Gilam and Dome Concordia and plotting the ratios, we obtain these figures here. We've also broken them down into time sectors. So Dome is at around 3 to 9 a.m. local time, and then we have 9 a.m. to 3 p.m., etc. And I say roughly because the stations are at different time zones, so they don't match up completely. I had to, well, get them into, there's a bit of fuzziness around the edges. Now, two things pop out. There's only more power in the south, where you see blue color, in the heart of winter, as you see here in December and January, and only at solar minimum. And also, there is a preponderance of extra power in the north centered at midnight here, and also at solar maximum and in the summer. If we look at noon, there's not that much power between hemispheres. I mean, we can kind of see a trend of more power in the summer and in the solar maximum, but it's not as pronounced as in nighttime, where the north dominates. And we tried the same for Seniliquat to make sure that there wasn't any problem with Gilam, although there might be some problem with Dome Concordia, which we can't really tell from this plots, but well, I'll try to see if I can resolve that in the future. But it fills up the gaps, and we see mostly the same thing. Now, if we look at power compared to azimuthal angle, we can see the distribution for Gilam here in the top, in the 4 time sectors as in the previous plots. You'll notice that the azimuthal angle never goes above 90 degrees at noon and never below 90 degrees at midnight. See, 90 degrees is when the sun is directly on the horizon. So these two sectors represent always daytime and always nighttime respectively. And the other two are more mixed, being at dawn and dusk. Now, looking at Dome Concordia, things aren't as neat as before. It's at around minus 75 degrees latitude, and so it is well within the Antarctic Circle. So there are times of the year when it will be nighttime at noon, and also daytime at midnight. By putting together the medians and quartiles from the previous figures, you can see that they more or less match up when the azimuthal angle is less than 90 degrees, so daytime, and they diverge often a lot during the night. Now, it is known that solar insolation affects solar precipitation, and there have been papers on that coming out recently. So this may be a demonstration of that effect. So the higher incidence of the aurora oval being within the nighttime in the south, leading to less power being precipitated through electrons at that time compared to the north. Turning to low L stations, we see a uniform, modest power symmetry all across the board in favor of the north. There's an outline here, but I think it's due to very low statistics. And looking at the azimuthal angle dependency, we also see a small preference for the north across the board. And that far from darting, the effect of solar insolation is probably no doubt minor. Finally, let's take a look at changes in the horizontal component of B, which is a useful proxy for geomagnetically induced currents. When comparing Gila and Dome Concordia, there is a massive discrepancy between the hemispheres, with the north experiencing DPDTs by up to an order of magnitude higher than the south. I mean, you take a look at the axis in the top panels and the south panels in 2015 at midnight. For Gillam, it reached up to 800 nanotesla per minute in some events, and more often up to around 200 to 300 nanotesla per minute. While in the south, it's mostly 40 to 60 nanotesla per minute. And you also see this behavior to an extent in solar minimum, and also at dawn and noon, although not as intense as at midnight. For the other high L stations, the difference is still there, but it's not as pronounced as before. So the DPDTs in the north are only about twice, or in some cases a bit even less than twice, higher than in the south. Now, bear in mind that although the magnetic latitudes seem similar, the location of the southern magnetic pole is closer to the South Pacific around New Zealand than it is, meaning that the station there is at much higher lower geographic latitude than the north. So the geographic latitude for Macquarie Island is around minus 55 degrees, I think, whereas it's minus 75 degrees for Dome Concordia. So it's well above the Arctic Circle. So it experiences far less extreme solar insolation compared to the other one, which may account for the difference. In fact, in this case, the northern station is the one closer to the Arctic Circle and the southern station to the Antarctic. And if we look at Barak versus, which is Russia versus, I can never remember how the other one's called, the one in the south anyway. Well, the northern station has easily twice the power as in the south one, twice the DPDT, sorry, as in the south one, pretty much across the board, which is pretty much what we'd expect from the previous measurements. And if we look at the last pair, where the southern station is at slightly higher L than the northern one, we have more or less parity, with a few occasions where we see a bit more activity actually in the south, right? Like here in the dusk sector in 2015. So in conclusion, we have performed a statistical analysis of multiple interhemispheric conjugate stations, or as conjugates as they can get when you're dealing with ground stations, over a hefty time period of one solar cycle. There's generally more power in the north, particularly when solar insolation comes into play when we have high L stations. And at lower L stations, there is a bit more power in the north in general, which is more uniform, but also less extreme than what we get in the higher L when we have these conditions, especially at solar maximum. The effect is also more prominent at local nighttime, in the summer, and during the solar maximum. Thank you. Well, this went a bit faster than I had anticipated, but I was worried about eating into people's coffee time, so maybe I talked a bit faster than I should have.
Okay, thank you, Stavro. Any question or remark? Konstantinos gives a thumbs up. Me too.
Yeah.
Yeah, I noticed that there are, the L value is not exactly the same. So there is a 0.3 difference between.
Yeah. Hold on.
So I'm not sure how much this could influence the difference. Of course, the differences are really impressive most of the time.
Yeah, especially when compared Dome Concordia with Gillam and San Killiquac. But there was one set of stations where the southern one actually had higher L than the northern ones, and I used that to check that we also see this kind of behavior when the L's are flipped. And I was also looking at a bit lower stations in the Churchill line, which I haven't put in this presentation here, and comparing them to Dome Concordia. So I was looking at one where that had an L equals 5.4, I think, in the north. And we also saw, and I could also see more power there in the north, but I didn't perform as robust an analysis with the other stations, so I didn't think to include it in this presentation. So yeah, the conjunction isn't good enough, but we can see that the trends are a bit more general than that, and they can probably carry over despite that difference.